theorem. So now we assume that M is compact. Again, M is X mod gamma, and here is an exercise. You remember there are two types of isometries. There are hyperbolic isometries and parabolic isometries. There are also elliptic isometries, but we need to consider them only when we consider orbifolds. Now we consider manifolds. It's an easier life for us. At some point, I would like to consider orbifold, but this maybe in next year course. So there are hyperbolic isometries and parabolic isometries. Parabolic isometries are indication of non-compactness. Actually, here is the exercise that I give you. If M is compact, all the elements of gamma are hyperbolic. So M, it's more than that. So first, it's if and only if M X mod gamma, so gamma is the spin group, is compact, then any gamma in gamma is hyperbolic. In fact, for this you don't need you can assume also torsion. So in fact, if I don't assume that M is a manifold, but only an orbifold, I would say that M, which is X mod gamma, is compact if and only then any gamma is semi-simple. It's either hyperbolic or elliptic. And this is, I think it's a good exercise. Remember, what does it mean that it's hyperbolic? It means that the displacement function attains the minimum. So that's, but any function on a compact space attains the minimum. So from that you can actually just take a compact fundamental domain and play with that, and it's not a hard exercise, it's good, I leave it to you. The second is that it's if and only if. So if M is non-compact, if the volume of M is finite, but M is not compact, then gamma admits a non-trivial parabolic element. So this is the second part of the exercise. Think about this exercise. Again, in next year's course, I will prove all these things when we study the structure of isometry group. But for now, just think about this exercise. And this helps us. Why? Because you remember that if we had that Margulis lemma allows us to deal tell us that what we need to understand is virtually important group of isometries. And if you have an important group of isometries, if you remember, if the group is not abelian, then you should remember that we show that if the group is not abelian, then in the center you can find a parabolic element. I remind you from last time that if N is an important group of isometries and of rank K, and K is bigger than 1, and is bigger than 1, so it's not abelian. So if you look at CK minus 1, in the central discrete series, this was consisting of parabolic. Parabolic and elliptic, actually algebraically parabolic elements. And now we don't have elliptic, so there will be parabolic. So the corollary is that if we are if the manifold that we consider is compact, then any nilpotent subgroup of gamma is actually commutative. So that's the corollary of this under this assumption, any nilpotent subgroup of gamma is commutative.
So you don't need to assume it's torsion free for that.
Torsion free to the hyperbolic.
No, here I assume it's torsion free. I assume manifold. All this thing is about manifold. The only thing that I say that it's true even without manifold is that star. But then instead of hyperbolic, consider replace hyperbolic by semicircle.
And the second one is not?
The second one is actually I think it is. Okay, we'll postpone it to the time when we speak about W. And okay, so what do we know about this? So we had another lemma. I recall you that we put the following lemma. If alpha and beta commute, so and they are both hyperbolic, then mean alpha intersect non-trivially mean beta. If you want, mean alpha is beta invariant, and then you can project everything there, and the projection is a beta invariant function. It's decreased. This is non-increased distances, and from that you can show that the displacement only decreases when you project, and so this will be non-empty. It's non-empty, and it's isomorphic to let's say to x. Let's call it W cross RK. Well, actually, K is 1 or 2. So it's actually W cross R or W cross R2. And both acts alpha. So if we call this, let's call it my minimum alpha beta. So each of them acts, and each of them both act by ID here and translation. Okay, I think we proved that. Maybe the proof was not complete because at some point in the proof I needed something equivalent to the flat strip theorem, the flat source theorem, so which I didn't prove, but we discussed that. We had this not just for two commuting, but for abelian group, which commuting not much. Okay. Now suppose we're in the following situation. Suppose that alpha and beta are both stable. So lemma, if alpha and beta, they are both in gamma, are stable, and d alpha less than epsilon intersect non-trivially d beta less than epsilon, then they commute. So why is that? So how does the hyperbolic element so recall how hyperbolic element act. So if gamma is hyperbolic, recall that gamma is hyperbolic, then mean gamma is a totally geodesic submanifold. It's a union of x's, is of the form some, I don't know, W cross R. And gamma acts on the set on W cross R by ID translation. So this is, if you want, this R is the axis, but maybe in negative curvature there's only one axis. In higher rank, in non-positive curvature, there may be many axes, and they are parallel to each other, and you translate along them. So that's how every hyperbolic element acts. What happened if we replace gamma by a power? So here on this set, it's obvious. It's still act by ID, and instead of translating by A, it will translate by Ka, the power of K. But maybe the minimal set will increase. If we take power of an element, maybe suddenly, on this it will still act like that, but maybe the minimal set will be larger. If we replace gamma by gamma to the K, then the minimal set of gamma to the K is now W prime cross R, where W prime may be a larger set than W. So maybe there are more elements. Suppose suppose even you have only one geodesic and you rotate around it. No, it doesn't fix anything else, but you rotate around it by some, let's say, rational rotation. So after you take the right power, suddenly some rotation become trivial. So you suddenly increase the more axis. Okay, but this will not happen if gamma was stable and the power was small. So now we can prove this lemma. Proof. So let's say if x, the condition d alpha less than epsilon intersect d beta less than epsilon non-trivially, implies by the Margulis lemma that the group alpha beta contains a normal subgroup, normal abelian subgroup of index less than m. No abelian subgroup, let's call it A, of index less than, right? Normal nilpotent. Margulis lemma says normal nilpotent. But now, by what we said, we know that nilpotent mean abelian, because we deal only with hyperbolic element. There are no parabolics, and so it has normal abelian subgroup. So now there are I and j less than m, such that alpha to the I and beta to the j belong to this commutative subgroup. So it means that mean alpha to the I intersect mean beta to the j by what we said somewhere here, because two hyperbolic elements that commute, and this intersection is W cross R or R2, depending whether the axes are parallel or not. Let's say R to feel stupid to call it K, k because k is either 1 or 2. And the action is, and both act by ID translation. Here. And that's the powers. Now we call that alpha and beta, we assume that they are stable. Alpha and beta are stable, and for stable element, the action is the same. A stable element, the minimal set does not change when you take a power, and only the translation change. So for stable elements, since alpha and beta are stable, mean alpha equals mean alpha to the I, and mean beta equals mean beta to the j, and the action alpha and beta acts on the same space. So this is at the intersection of mean alpha with mean beta now. So it acts on W cross RK, but each of them act by ID, and the same translation as before divided by I. So alpha act by this divided by the same translation of let's say that we had here of alpha to the I, but divided by I. It's a Euclidean space, you can divide. And beta acts on W cross RK by ID, the translation of beta to the j divided by j. Okay, so two translation commute. This implies that alpha and beta restricted to this subset commute. So, and this implies that the commutator alpha beta, alpha inverse, beta inverse has a fixed point. Has a fixed point. Because the commutator, they compute on this minimal set, so all this minimal set will be a fixed point, and its minimal set is non-empty, but the action is free. But the gamma acts freely, which implies that alpha and beta commute. So now we are in a really good shape, because everything, locally everything commutes. Okay.